Now we're recording. So, okay. How's the homework coming?
Struggling
Was that
with
number
number two.
C exact equation? Way to solve it? I've got it.
Part C.
Yeah.
No.
No, for
Really?
4C
I thought it
was
was
the
exact.
one. Yeah,
It-
4A
it-
was.
it-
4C wasn't.
Yeah.
And then you
It
got-
bare. Yeah. Well, in fact, A is even separable, so it's
Right,
even
right.
easier than that.
That was pretty good.
Um,
Oh, yeah, exact.
C just barely misses being exact. It's quite heartbreaking.
With the plus and the minus?
Yeah. Yeah. So that's where you have to. That's why I took some time to do the integrating factor approach, and it's a bit painful, but it does work.
I thought it was hard, so I skipped it and decided to jump onto 1, 2. And then it was, number 3 was hard.
Well, okay.
But, yeah. I mean,
Now, if you look at the notes that I just posted for today's class, because today we're finishing chapter 1. Now, it seems a little ambitious to cover sections 1.3, 1.4, and 1.5 all in one day, but each section is ridiculously short. I don't know why he even made them separate sections. So we will. There's actually not much in the way of notes, and at the end of those notes are the last problems that go in this assignment. There's not much. So now we have. So there's a grand total of 1, 2, 3, 4, 5, 6, 7 problems altogether, or parts thereof. And all that is due a week from Wednesday. Hopefully, it doesn't spoil your Labor Day weekend plans that much.
For math majors, we don't have plans.
I mean, some of you may have been wanting to go to the football game this weekend
I'm going.
and see us get creamed.
I'm going, like,
Hey, I don't know how I feel about the 9 o'clock start time. It's a little off-putting.
you of course said that.
regardless of the outcome, people are probably going to end up having a good time regardless. So
Oh yeah, definitely.
probably the thinking behind the late shift topic.
Yep. Okay. So we'll go through these. We'll blast through these 3 sections, and if there's time left over, and there just might be, then we can talk about the homework problems. Okay. Let's see. So, so we have a system of ODEs of this form, most general form. Is autonomous if a vector field X is independent of T. So in other words, just have x little x prime is equal to big X of little x. So big X itself does not depend on T. So example, if big X of x1 and x2 has these components, like x1 times x2, well, plus x2. Now little x's, they will always depend on T, but big X itself has no direct dependence on T, therefore we call it autonomous. Those are the kind of systems we prefer to study. For the most part, we will, but I do need to say a little bit about non-autonomous. So vector field X is time dependent, if X has a domain, which I'll call B, that really belongs to Rn plus 1, and it maps into vectors in Rn. So the idea is this domain includes space and time. So we have one time dimension, then n spatial dimensions. But it's always mapping to vectors in space. All right. Now the thing is, for each value of time in this domain, we can, it turns out that the spatial part of the domain might vary. So we say a slice of B, we put the subscript t in there. So we're taking cross sections for each possible time. So it is a portion of space such that for this particular t value, so the thing I want to emphasize is we have some fixed time value here. And we're seeing for that fixed time, which x's belong to the domain of our vector field. So this reinforces the point that as time moves forward, the domain of your vector field may change. Now I'll give a simple example of that. Okay, so we have like a time-dependent vector field with two spatial variables. And I'll give it these two components. Okay. Now, let's see. So what's going to happen here is, let's consider a case where t is equal to 0. Well, as you can see here, when t is 0, the vector field is undefined because of this division by 0. So that means that our time slice, we're going to call it b0 because t is equal to 0 in this case, is empty. So that can happen. For a certain value of time, the vector field might be completely undefined, so you have an empty slice. Now, when t is non-zero, we want to, so our slice will be, instead of all x and y in R2, in our spatial domain, as long as x and y satisfy certain conditions. So what limiting conditions are there on either x or y that would limit membership in this, this slice? So I'd put these conditions here.
X cannot be equal to t, right?
Right, it can't, but what else is there?
X can't be less than or equal to 2.
Right, so x has to be
Right.
strictly greater than t. It can't be equal to t because of division by 0. It cannot be less than t because of square root. And there's no restriction on y here. Y can be whatever it wants. So as long as x is greater than t, then that is your slice. So what happens is, as t increases, your slice is shrinking somewhat because you're losing a little bit more of x. Okay. So if you fix t, then, and once you know what your domain is, then you have an ordinary vector field, like a time-independent vector field, for that particular value of time. Okay. Now, so now if we have a time-dependent vector field, like we do in this case, so this is a non-autonomous dynamical system when there is an explicit t-dependence. I think we've only seen one example of that so far. It was a constrained ball in a hoop was an example of a non-autonomous system. Okay. So we have a non-autonomous system. We need a rigorous definition of what is a solution of such a system, but really, that's going to be essentially exactly the same as what happens in the case of an autonomous system. Well, at least it's getting easier and easier to video my classes. It was a real pain before, so maybe I should just tape all my classes if I'll never have to lecture ever again. I'll walk into class, I'll write the link to the YouTube video and leave or something like that.
Hey, I mean, or you when you have one class, just email it.
It's
Chances are,
better to make sure people are like coming to class, just like put it on like this.
you put it on the screen.
Yeah, just put it on the
Yeah,
screen.
but-
Be like, and just sit there and just watch yourself talk and be like, yeah, that was a good point. Like that's what I would do.
Then you can critique yourself enough you need to redo the lecture.
Yeah. So. Yeah, because, well, I probably still have to come.
Why? So you don't get in trouble for not lecturing?
Yeah.
Well, you could post a sign on the door that says class in session.
Do not disturb, yeah.
Or you could come and just like
Nap.
sit- Yeah, like you could come and just do something else. There are so many ways to get
Okay,
around
that's probably allowed, or at
Yeah,
least
you could
it's
come.
not
There's
expressly
so many ways to
forbidden.
get around it, you just haven't tried yet.
And now I've just said this on tape.
So you edit that part out.
Okay, I'll think about it. Well, it's all hypothetical anyway. So.
Okay.
Well, I mean, I have a full set of lectures for 280 and now 610, and I'll have 605.
You're
So.
welcome.
Yeah, I know. Yes, everybody, I used her iPad
yeah.
after many other things failed. Okay, so solution, and of course this is known by many other things, also known as a solution curve or integral curve. Of a non-autonomous system little x prime is equal to big X of t and little x. Is a differentiable curve R, which maps some interval in time into Rn, and so assume that the interval I is AB, which it could be an infinite interval. That's allowed. So it has satisfied a condition that the tangent vector is equal to big X with that same value of time and that and the point in the curve plugged into the vector field for all values of t in the interval. Really, I barely even needed to give this definition because it's so similar to the definition of a solution of an autonomous system. It just said you're plugging in that particular value of t into the vector field as well as a curve. So there's really nothing of interest. But you also have to be sure that each vector r of t has to be in the domain of definition of a vector field big X. But if you don't have this, there's no way on earth you're going to have that as well. Okay. Okay. And finally, another essential definition that comes out of this section, and this is something that you dealt with in your first differential equations class, because this solution, as I've defined it, whether it's for autonomous or non-autonomous system, is not unique. As you've seen in plots of vector fields, you have all of these streamlines, or also known as solution curves or interval curves. There are infinitely many of them. Now, if you have an autonomous system, at least those are not self-intersecting. So, what does it take to make a solution unique? And this leads to, which is likely a familiar concept, of an initial value problem. So an initial value problem, also known as an IVP, and I'll likely refer to it that way in the notes from now on, is a system that could be autonomous or non-autonomous, doesn't matter. I'll use non-autonomous here because it's most general. So it's any kind of dynamical system with an initial condition that nails down the value of the solution at some initial time. And what it's equal to is called the initial value, or initial point, or initial data. We mathematicians like to call things by so many names because we just can't agree on anything. That's pretty much the way it goes. Okay. So a solution curve, or a solution of an IVP, is nothing more than a curve that satisfies a solution. So it's using a previous definition of a solution as a solution curve. that also satisfies the initial condition. Okay. Now, what we will see later is a theorem, very important theorem from ODEs called the existence uniqueness theorem, that specifies under what conditions a system like this, with this kind of initial condition, has a solution that exists and is also unique. So most of the time, most problems we deal with, we specify initial condition that nails down a unique solution. So I'll give a simple example of an initial value problem. This is something you would have come across in earlier calculus and physics classes. So I'm going to write a second order ODE. So my unknown is P. P refers to position. And I'll assume that it's equal to minus G, constant of gravity. Okay. And I actually have, because it's a second order equation, I actually need two initial derivatives. So my initial position, I'll call P naught, and then I need to specify the first derivative at the time. So second order ODE needs initial values for the function itself and the first derivative, and this will be V naught. So V I'm using to refer to velocity, which of course is P prime. So this is a well-formed, well-posed second order IVP, but I want to describe this in using a terminology that I've been using as a first order system. So any higher order system can be rewritten as a first order system. So I say that P prime is equal to V for velocity, and then V prime, which is the same as P double prime, is equal to minus G. And then P of 0 is P naught, and V of 0, which is P prime, that would be V naught. So now I have a first order IVP, which has a unique solution. And in fact, what would be and you may notice, probably remember the solution from prior classes, what would the solution be? Well, for instance, if V prime satisfies this, everything here is a function of t. So, so what would V be? That would satisfy this and the initial condition.
Negative GT.
What?
Negative GT.
But that's not the whole thing.
Plus something.
Plus what?
V naught.
Yeah, plus V naught. Okay. And now, going back to this, what is the solution for P?
VT.
GT squared.
Even though it doesn't come to you right away mathematically, you might remember from your physics class or something.
VT plus P naught.
VT plus
That's part of it.
Okay.
Negative 1/2 GT squared.
Yes.
Oh, I
Those
just.
are the
Ah,
Yes.
now I'm
Yeah, you
an
just hit
idiot.
one of those
Oh, yeah.
See, I know some people know that, or that rings a bell. anyway, plus V naught T plus P naught. And that is the unique solution. It's the only solution that satisfies both the ODEs and the initial conditions.
I try to forget a lot of that.
I don't blame you.
I mean, bad memories.
Oh.
Yes, same here. Okay. All right. Okay. Is there any questions about the concept of initial value problem? Okay. Now, well, that particular system was autonomous, since there's no direct T dependence. Okay. I was paranoid to make sure it's still recording. Oh, I guess it is. All right. Now, simply because it's covered, I find sometimes the ordering of the material in the text to be a little strange, because in 1.3 it's all about non-autonomous systems, and 1.5 is also about non-autonomous systems and what you can do to simplify matters. But then 1.4 is only about autonomous systems. And I think I would have done things in a somewhat different order, but anyhow. All right, now that we're using the language of vector fields in order to describe systems of ODE, which we were not doing at the very beginning, I can give a more rigorous definition of fixed points, which are also called so many other things. Stagnation points, stationary points, equilibrium points. And in fact, one more was thrown in here, critical. So now we have 5 terms for the same thing. Now it's just insane, but what can I say about my fellow mathematicians? We are insane. Okay. So if you have, now this is only for, I can't stress this enough. Only. The concept just makes no sense if you don't have an autonomous system. So let's suppose we have a vector field X that maps some domain D in Rn into Rn. So some point C that's in that domain of your vector field, and I'll just use fixed point, it's my favorite one of these terms anyway. Also the easiest one to write. Of really, not of X really, but it's of the autonomous system, little x prime is equal to big X of little x. If C happens to be a root of X. So what that means is a solution curve, if you know a fixed point, is just R of t is equal to your fixed point for all t. Because what happens is r prime of t is going to be 0 because we have a constant vector here. So the derivative is 0. And then you plug in r of t. Okay, so r prime of t is 0. So then you look at big X of r of t, but that's going to be x of c, but x of c is 0. So the two sides agree, they're both 0, so that's why it qualifies as a solution curve. So it's the most uninteresting solution you can have, but it's a solution nonetheless. Now, in the majority of cases, so what you have to do to find a fixed point, you have to solve that system of equations. It's going to be n equations, where n is the number of spatial variables. So usually, you have no choice but to find these numerically, using whatever methods are out there for finding zeros of functions. Now, since we're talking about functions of several variables, the best methods would be something like Newton's method, or generalizations of the secant method, things like that, or fixed point iteration. Those of you, let's see, I guess half of you are taking 560, and the other half of you already took it. So those kind of methods are covered there. We don't really need to get them here. Although I did give a homework problem from this section, with some autonomous systems where you actually can find these exactly. So at least sometimes you're able to. Okay. All right, so at least now we're on record with a more formal definition of fixed or stagnation or stationary or equilibrium or critical points than we had before. Okay.
So for the homework problem, on this section, we're gonna find all the fixed points A through D.
Right.
Okay. First, we're gonna find the integral curve, right?
No.
No?
Yeah, that's nicely. You don't have to solve a system. You're only looking at the given time derivatives and seeing where those time derivatives are equal to. What x and y, for instance, make all of them simultaneously equal to 0. Okay. Actually, yeah, I'll do a simple example. Oops. And I have no idea, since I'm just making this up right now, if this happens to resemble one of the homework problems. If it does, well, that's a gift, I guess. Okay. So suppose we have x prime is equal to x plus y, and y prime is equal to okay. Okay. So what you do is you take both of these time derivatives and you set them equal to 0. So x plus y is 0. 3x plus 2y is equal to 0. This is a linear system of linear equations, two equations, two unknowns. And it's non-singular, so this is actually going to have a unique solution. So from this equation, you can conclude that x is equal to minus y, and plug that in here, so then you have minus 3y plus 2y. Oh, that's not going to be very interesting at all.
Maybe y equals 0.
That's okay. Corey. What?
Okay, Okay, I'm gonna change a little bit. Okay. Okay. All right.
What did you add on?
I threw in a +5
5.
on the y derivative there. Well, okay, but still my point stands. It does have a unique solution. It'll just be slightly more interesting than what it was going to be before. So now we have,
Y equals 5.
yeah, so y is equal to 5, and therefore x is equal to -5.
But it would be like both 0, right?
What?
Like in the other case, it would be y equals 0, x equals 0.
Yeah, it'd be a trivial solution.
Yeah.
So, yeah. So this is the one and only fixed point. So that's really what you can expect from typical linear linear systems. Well, we could have no solution, infinitely many solutions, or unique solution. It breaks down in both categories. But there'll be some examples, probably on the homework, where there's a nonlinear, but still something that could be solved algebraically. Okay. So questions on that one? Okay. And now it's 1.4. A one-page section. I don't understand it. And later on in the book, like there'll be one section that's like 30-something pages long, one section. So I don't know how he decided to distribute his material, but whatever. Okay. Now, so we've seen first order systems, we've seen higher order systems, like in the earlier example. We've seen autonomous systems and non-autonomous. But really, as far as developing theory, we really only need to think in terms of first order autonomous system. That is the only truly interesting case because any other system can be reduced to it. So suppose you were given a higher order system. We'll say it has order m. Okay. So some function f, little f, I want to emphasize, as function of t, x, x prime, x double prime, and so on, all the way up to derivatives, time derivatives of nth order is equals 0. So that's about as general as I can get. That little f is allowed to be any function that depends on t, so I'm assuming it's not autonomous, and then depends on x and all its derivatives up to order m. Now, in order to be able to reduce to a first order autonomous case, what I'd like to be able to do first is rewrite in this form, where the highest order derivative, instead of all the x's and all the derivatives being independent variables, I would like my highest order derivatives to be dependent variables. So I want something like this. So here I have big F, dx, x prime, x double prime, all the way to xm minus 1. Now, can we always do this? Unfortunately, no. but I can describe conditions under which this is possible. In other words, basically, we want to be able to solve this equation for this variable in terms of all the other ones. So what we need in order to be able to do that is little f, and I'm going to make these variables generic now. So I have v1, v2. Actually, I want to make sure my notation is consistent. No, I started numbering at 0. v1, v2. So what happens is now I have just generic independent variables here. I need to satisfy these conditions. Okay, also, this is a vector valued function. So the right side of this is in Rn. Okay. So I have to look at each component function. So little f is and big F also, these are vector valued functions. And they both have n outputs. So I'm looking at each component function of little f, and I'm taking a partial derivative with respect to each component of this last variable. So Vm, but I'm looking at the jth component of this. So what happens is, if I'm looking at each component function and its partial derivative with respect to each component of Vm, for all possible ij, so I and j are ranging from 1 to n. So all of these partial derivatives arranged together give me a matrix. So the component functions of little f give me the rows, and these components of Vm that I'm taking derivatives with respect to, those give me the columns. So I have this Jacobian matrix but it's not the entire Jacobian of little f. The entire Jacobian have derivatives with respect to all of these guys. But I don't want that, I only want this one. So this is a square matrix, and that Jacobian matrix has to be invertible. So if it is invertible, then I'm able to solve for this last variable in terms of all the others and write the system of ODEs this way. And this theorem that outlines this requirement is known as the implicit function theorem.
You're saying it's a square matrix, so I equals j eventually, or
I'm sorry, what?
you're saying it's a square matrix, so it's n
Yeah.
by n.
Yeah, n by n, yeah. And you're looking at all possible ij's from 1 to n. Okay. Now, to give you an idea as to why this condition is important, I'll just scale this down to a case where x and its derivatives are just scalars. Okay. Okay. suppose you have a situation like this where you have little f of, I'll go with just two spatial variables is equal to 0, and you want to go from that to y is some function big F of t and x, and you want to know when you can do that. Well, if you take this representation of of y and plug that into here, so now everything is a function of only t and x, where you don't know what big F is yet, you're just hoping it exists. So the question is there a big F that satisfies this? And like in terms of an explicit formula. So what you can do is differentiate this whole equation with respect to t. And what you get is partial of little f with respect to t plus partial of big F, well actually partial of little f with respect to y, partial of big F with respect to t is equal to 0. And then you also differentiate this with respect to x. So partial of big F, partial of little f with respect to x plus partial of little f again with respect to y, partial of big F with respect to x, also is 0. So the way that your big F can be defined is in terms of its derivatives. So partial of big F with respect to t is minus partial of little f with respect to t over partial of little f with respect to y. And similarly for partial of big F with respect to x. So this is really just a chain rule at work. And what do we have in the denominators? Partial of big F with respect to y. In this case, the Jacobian matrix I mentioned over there is just a 1-by-1 matrix. It's just a number, or a single scalar valued function. So both of these,
Negative?
what? Yeah, there must be a negative because of a plus sign over here. So this partial derivative of little f, sorry, on the right-hand side of these equals, it's all little f's. Yeah, unfortunate choice notation, again, be consistent with the book, silly me. These partial derivatives of little f with respect to y must be non-zero in order to make this work. So that's the only time that you can perform this inversion, if you will. So it's relatively easy to see in the case of a scalar valued function, whereas if I had several unknowns here, my system would be a lot more complicated, and what you'd end up with is a system of equations involving an actual coefficient matrix, and then that coefficient matrix would have to be invertible in order to be able to solve the system that's a lot easier to solve in this case. All right, so that is basically the implicit function theorem at work. I wonder if you actually might, well, I think almost all of you are taking real analysis right now. You're not, and you already did. Okay, so you are, or you did it before, and that might come up in there. Okay. All right. So what we're going to do from this point is I'm going to assume that. Okay, I'm not going to erase this board. I just want to turn back to it for a bit. Okay. So going forward, we're going to assume that this most general M-folder system can be rewritten in this form. Now I want to see how can we reduce this to a first-order autonomous system. So now we have highest order derivatives is equal to big F of t, x, x prime, x double prime, so on, all the way down to m minus first derivative. So all right, so reduced to first order. So we do that by introducing new variables. Okay, so I'm going to let okay. Vi be equal to the ith derivative of x, 1, 2, all the way up to n. What?
Well, there is only up to n minus one, right?
Yeah, that's all I need there.
Right.
Okay. So for instance, for a second order system, I only need to introduce just one new variable. So the first order system that I have is so x prime is equal to v1. v1 prime is equal to v2 because v2 is x double prime, but v1 prime is also x double prime. So it just cascades like this. So v2 prime is equal to v3, and so on until we get all the way to the end. So vm minus 1 prime, well, that's going to be so if I take a prime of this, it's going to be xm, but now the vector field comes into play. So t, and then we have x, and then for higher order derivatives, all the v's sneak in there. So it's v1, v2, and so on, all the way down to vm minus 1. So now it is at least reduced to a first order system. So however many higher order derivatives you have, that's how many new variables. And if your solution is in Rn, each of those new variables also is a vector in Rn. Okay. But then I want to make it autonomous also. And for that, I introduce one new variable. I showed you this before, but just to summarize everything, I have a variable tau prime is equal to 1. So therefore, tau itself is going to be t plus a constant. So then I can use that up here, and now I have tau. So now there is no direct dependence on t. So these are all the new variables we need to introduce, and therefore any, at least any dynamical system of this form, higher order and non-autonomous, can be always reduced to first order and autonomous. So that's why we're only going to assume first order autonomous, however many equations it has, in order to study the behavior of solutions.
Did you just erase the T and put the down there?
Yes.
Okay, that's what.
So hopefully the arrow's a reminder that there was at one time. Yeah, because tau is t. Okay. Questions? Homework questions. Since we still have some time. All right.
How many problems are there from the dissection 1 and 2?
Okay, so there's one problem. So number 1 and 1.3, number 1 and 1.4, and then from 1.5 there's problem 1 and problem 3. So there are 7 problems altogether. Lots of them both have
You
parts.
said you posted this notes on them?
Yeah, we're posted now. Oh yeah, one thing I want to make sure of,
So-
if you guys are frequently visiting the site, make sure you reload the page.
Oh, there you go.
Okay. And that happens a lot where,
Yeah, it was in cache probably.
yeah.
I don't know if you could do an example of this.
Oh, yeah. Let's see.
Even if we leave the two, so.
Okay, I'll just, alright, so higher order and non-autonomous. Okay, so let's assume that y double prime is equal to, okay. Okay, something like that. So this is second order non-autonomous. So first thing that's done, since we are one order differentiation above first order, so we need one extra variable. So I'm going to let v equal to y prime. So now our first order system of 2 equations is going to be y prime is equal to v, and then v prime plays the role of y double prime. So whatever you had here before stays the same, except that but now wherever you see y prime, you replace it with v. So you have 1 over t times v minus e to the t y. So you only have first derivatives on the left side. You have no derivatives on the right side because you're using your new variables. And then to reduce it further to an autonomous system, I have the equation tau prime is equal to 1. And then in your other equations, wherever you see t, you just replace it with tau. Okay, so this is your final product, whoops, that's v prime, not v double prime. Okay. First order autonomous system. So it takes 3 equations altogether.
So if there are no t's, we don't need tau's in it, but there are t's in it.
Yeah, so the t's get replaced with taus.
Right.
Yeah, so really it's the addition to this third equation that makes it autonomous. And the thing is, so at least at this point, because it's autonomous, well actually here's a funny thing about how I mentioned that it doesn't really make sense to talk about fixed points for a non-autonomous system. And in fact, are there going to be fixed points in this system?
This is autonomous, right?
Yeah, so it makes sense to discuss fixed points for this system, but are there actually going to be any? Because to be a fixed point, you have to make all the time derivatives equal to 0.
You can't have that.
Yeah, this equation kills it right
Yeah.
there. So since that is always going to be non-zero, you would never have a fixed point for a non-autonomous system. So even converting it to autonomous doesn't do you any good. Other questions at all? So everything will just go swimmingly with the rest of the homework?
Of course, that's exactly how that works.
Yeah.
Until you start getting text messages.
Yeah. Gosh, Clarence, what is
Okay. Well, I'm used to it. Most of it, plus, you still have plenty of time, so, and, well, 4 of the problems you haven't had a chance to really look at yet, but. But make sure that you, have a chance to look at it, for, Wednesday, and at least just to make sure, like, do you feel good about what the problem is asking, that, you know how to start? Because Wednesday is the last class we have before these things are due.
Right.
Since we don't have, Labor Day, but,
Maybe if you're free after class on that day, we can just, however many people are free, just come by.
okay, yeah.
Bombard you with
Oh,
questions.
yeah, once adult have to go to real analysis anyway.
Oh,
Well, half of you do.
okay,
Yeah.
right, so,
Oh.
yes.
Yeah, well, but again, I'll probably be around even after real analysis gets out. So. I'm usually here till around 7 p.m. on
How long
Monday
do
through
you
Thursday.
have that, how long do you have
It's
that?
an hour and 15 minutes, just like this one.
Well, this way.
Yeah, you're one of the lucky ones. That's-
Yeah,
Yep.
or the unlucky ones, that depends, because they still gotta be on class and
Oh, yeah.
can't do homework, that depends on, right?
Alrighty. Yeah. Well, whatever you want to do is, I mean, I'll be around.
Right, right.
So, okay. And then next time we get into chapter 2, so there's a touch of numerical methods, but not very much there. So, all right. Well, I guess we're good then. If there are no questions. Okay. At least I'll have so much